Hello everyone, welcome back to the course on measurement and instrumentation, and this is the third module of the course where we are discussing about transducers. We discussed about piezoelectric transducer in our third lecture of this 8th week, and today is the fourth lecture of our 8th week, and today we will continue our discussion on piezoelectric transducers. Okay. In the previous class, we have seen that the magnitude of piezoelectric effect in a simplified form can be represented by the vector polarization, and we have seen the equation P equal to Pxx plus Pyy and Pzz, where x, y and z refers to a conventional orthogonal system related to the crystal axes. Okay. In terms of axial stress sigma, we can write Pxs as d11 sigma xx plus d12 sigma yy plus d13 sigma zz. Okay, I am calling this equation 2, and similar to this you can write other equations of Pyy and Pzz, where Pyy can be again written as d21 sigma xx plus d22 sigma yy plus d23 sigma zz, and Pzz is equal to d31 sigma xx plus d32 sigma yy plus d33 sigma zz. Okay. In these equations 2, 3 and 4, the constant dmn, where m can vary from 1 to 3 and n is also varying from 1 to 3, okay, are known as the piezoelectric coefficient along the orthogonal axes of the crystal cut. Okay, we'll learn about this dmn in more detail in the coming slides. Okay. Right now, I am calling it just a piezoelectric coefficient. We'll give it some special name for the piezoelectric coefficient also. Okay, so we may not call it piezoelectric coefficient later on. We may give it some specific name. Okay, but for the time being, let's call it in generic form a piezoelectric coefficient. Okay. Now, dimensions of these coefficients are in terms of coulomb per Newton, or C per M, which is coulombs per Newton, that is charge per unit force. Okay, and the convention is that the first subscript in the dmn, okay, the first one refers to the direction of electrical effect, and the second in this is mechanical effect. Okay, so the direction m, okay, say let me take one example, say d12. Okay, so this 1 and 2 represent the first one, this one represent the direction of the electrical effect, while the second one is the mechanical effect. Okay, so dmn basically suggests how efficiently mechanical energy converts into electrical energy. For example, consider a piezoelectric ceramic, for example say PZT, okay, where say d33 is equal to 100 picocoulomb per Newton. Now, this value suggests that if a force of 1 Newton is applied along the Pauling direction, the charge Q will be equal to 100 into 10 power minus 12 coulomb, or say 100 picocoulomb. Okay. So, if you note this expression, even a small force of the order of say 1 Newton, okay, is able to produce a charge say of the order of 100 picocoulomb, which is a measurable quantity. Okay. So, what you are doing is applying a force, and the direction of force is shown by the second term here. Okay, and you are able to generate a charge say of the order of 100 picocoulomb, which is of course shown by the first quantity, say 3 here. Okay, and it shows that even you have applied a very small force of the order of say a Newton, then also you are able to generate a certain charge which can be measured. Okay, I hope that you remember that in the previous class we have discussed that how I can measure these charges by making say physical electrodes which can collect these charges. Okay, right. So, the subscript in the piezoelectric coefficient here indicates the direction coupling between the electrical and mechanical domains. Okay. Now, first subscript here specifies the direction of electric field, or you can say polarization, while the second subscript, the N1, okay, specifies the direction of the applied mechanical stress, okay. So in the expression, the Mn, this M is specifying the direction of electric field, while this N is specifying the direction of the applied mechanical stress, okay. So if I talk about D33, for example, mechanical stress is applied along the polarization axis, resulting in maximum charge generation, because both the values are 3, okay, means that mechanical stress and electrical field or electric field direction or say polarization directions are same, okay, means that a mechanical stress is applied along the polarization axis, which means that you will have maximum charge generation, and this mode, D33 mode, typically exhibit the highest piezoelectric response. And you will see that most of the piezoelectric material, if you read its specification, the D33 value will be specified for that particular thing, okay. Along with that, there is another term D31, which suggests that mechanical stress is applied perpendicular to the polarization axis. So this is the mechanical stress, and the first term is the electrical polarization axis, okay. So the mechanical stress here in the D31 term is applied perpendicular to the polarization axis. This configuration, D31 configuration, is basically widely used in bending and flexible devices where transverse deformation produces the electrical output, okay. Now the piezoelectric materials are anisotropic, okay, meaning that their property varies with the direction. So it may not be same along the, say for example here, the piezoelectric coefficient may not be same along say x, y and z direction. They might be different, and that's why you have seen so many different piezoelectric coefficient, okay. So the alignment between the polarization and applied stress plays a critical role in determining the efficiency of the electromechanical conversion of the mechanical force into the electrical charge, okay. We have this D33 and D31 mode. Say a D33 mode is sometimes also known as a longitudinal mode, okay. So in the longitudinal mode, the applied mechanical force and the generated electric charge that we have just seen are aligned along the same axis, okay, as the material's polarization. This alignment enables the highest efficiency conversion of mechanical to electrical energy that we have just seen, okay. But we have to understand that why D33 is preferred for any engineer, okay. So if you talk about any mechanical engineer who is dealing with the piezoelectric transducer or electrical engineer, you will see them talking in terms of D33 of the material, okay, because it has highest piezoelectric coefficient, okay. So typically they exhibit the strongest material response. So D33 high means highest piezoelectric coefficient. You have maximum sensitivity along this mode, so it produces larger electrical output for a given mechanical input. We have just seen that both are in the same direction, so you are getting maximum polarization for the applied stress, okay. And you have strong electromechanical coupling, which means that it enhances actually energy transfer efficiency, making it suitable for high performance sensing and actuation applications, okay. Then the second mode which we have seen was D31, which is the transverse mode, okay. So in this D31 mode, the generated electric charge develops perpendicular to the direction of the applied mechanical force that we have seen. This arrangement is particularly advantageous in the bending or flexible device structures where the mechanical deformation is producing, say, some amplified transverse strain, okay. Now such structural amplification enhances the effective piezoelectric response, and that's why D311 is also important, okay, along with the D33, okay. There are some other modes that is beyond the scope of this course, but if you are interested, you may read some good book on piezoelectric devices. There are certain books which are only on piezoelectric transducers, okay. Now we have seen one piezoelectric coefficient D33, or say in general we have seen Dmn, okay. Now let's see one more coefficient which will actually help us in defining a piezoelectric material or piezoelectric transducer in little more detail, okay. let's call it a G coefficient. Okay, this G coefficient is defined by a division of corresponding Dmn coefficient by the absolute dielectric constant. So if Dmn is say a certain piezoelectric coefficient, now if you divide this with the say Dmn is the piezoelectric coefficient. Now if you divide this with the absolute permittivity, which is epsilon naught into epsilon r, where epsilon naught is the permittivity of free air and epsilon r is relative dielectric constant of the material. So if you multiply them and then divide the Dmn value, you will get the corresponding G coefficient or Gmn. Now to differentiate between them based on their definition, I am calling this Dmn as piezoelectric charge coefficient now in place of piezoelectric coefficient. Okay, so Dmn is now called as piezoelectric charge coefficient. Okay, now this Gmn is a new quantity that we have, or new term that we have introduced, and this coefficient represents a voltage gradient or basically electric field generated by the crystal per unit applied pressure or stress. Okay, now the charge generated by the piezoelectric crystal is proportional to the applied force. Say for instance, in the x direction, Q is directly proportional to applied force. Okay, and if I want to introduce, or if I want to equate them, I have to write Qx equal to a constant K into Fx, and this constant K is nothing but D11. Okay, because I am applying the force in the x direction and wanting to find the charge along that particular axis. Okay, so this K is nothing but D11. So Qx is equal to D11 into Fx. Okay, so let me call this equation 5. Okay, Gmn is equal to Dmn by epsilon naught epsilon r. This is our fifth equation. Okay, now this value Q equal to D into Fx, say I am calling this equation 6. Okay, so Q is equal to D11 or Qx equal to D11 into Fx. Okay, since a crystal with deposited electrode forms a capacitor having capacitance C, voltage V which develops across between these two electrodes can be given as V equal to, or Q, we know that Q is equal to CV, so V will be equal to Q by C. Okay, Q we have calculated from equation 6. So let's put this value, say we have seen Q equal to CV for a capacitor. V will be equal to Q by C. Okay, so let's put the value of this Q in this equation. Okay, I can write V equal to D11 by C into Fx. Okay, I am calling this equation 7. All right, now we have seen that the piezoelectric effect is direction sensitive because it is an isotropic phenomena. Okay, so a tensile force produces a voltage of one polarity, while a compressive force will produce a voltage of the opposite polarity, and that is also very much clear from equation 7 also. Okay, the magnitude and polarity of the induced surface charge are proportional to the magnitude and direction of the applied force F. Okay, and the polarity of the induced charges depend upon the direction of applied force. Okay, now consider this structure where you have two electrode and the width of this is T. Okay, and a force, compressive force for example here, is applied here, and output, the dimensions are shown over here, and E naught is the output voltage. Okay, charge we have already seen from our previous equation, that is equal to D11 into Fx for generation in x direction, and in general I can write charge Q is equal to D into F. Okay, where D is the charge sensitivity of the crystal, which can be written in the form of say Coulomb per Newton, while F is the force applied in the Newton. Okay, now the force F causes a change in thickness of the crystal, and say it is delta T. F can be written as A into E by T into del T, where E is the Young's modulus and A is the area of crystal in meter square, while T is the thickness of the crystal. And let me call this equation as equation 8, and let's see that how we are concluding this equation. Okay, So for this we have to understood or we have to recall the definition of the Young's modulus, and here say Young's modulus E say is given as stress by strain. Okay, stress in this case is given as force by area, okay, which is divided by the strain, and strain is this del T by T, all right, and this is equal to the Young's modulus, and Young's modulus can be given as F by A into T by delta T, okay, and then if you want to calculate this F, it can be given as E into A del T by T, right, and this is what we have seen in our equation 8, all right. In this case, this W is the width of the crystal and L is the length of the crystal, okay. We have already seen from previous equation that charge is equal to Q is equal to D cross F or D multiplied by F, okay, and say I am calling this again equation 9, and from equation 8 we have seen F is equal to AE by T into del T. Now from these two equations I can calculate this Q in terms of the applied force, or Q is equal to D into AE into del T by T, okay. Just by replacing the value of F from equation 8 in this equation 9, I will get Q is equal to Q basically in terms of this force, which is equal to D into A into E into del T by T. Let me call it equation 10, okay. Now the charge at the electrode gives rise to an output voltage E naught that we have seen here at the output, okay. So E naught in terms of the capacitance between the electrode can be written as E naught equal to Q by Cp, and I am calling this equation 11, all right. So voltage E naught is equal to Q by Cp, and Cp, as I have mentioned, is the capacitance between the electrodes, and it can be simply written as epsilon R epsilon naught A by T, okay. So this is the capacitance, simple parallel plate capacitor, okay. So I am calling this equation 12, okay. Now I have the value of Q, E naught and capacitor, okay. Using these three equations and solving for the voltage E naught, I can say that E naught is equal to dt into F by epsilon R epsilon naught by A, okay. And let me call this equation 12, or we have already taken equation 12, so let me call this equation 13, okay. So this is equation 13, E naught equal to dtf by epsilon R epsilon naught into A, okay. Now in this equation, F by A basically is the pressure, or you can say the stress, okay. In this equation, F by A is the pressure component or say stress, okay. So E naught is equal to dt by epsilon R epsilon naught, and I am replacing this F by A by P, okay. So E naught is equal to d by epsilon R epsilon naught T into P, and let me call this equation 14, okay. Now if I replace this d by epsilon R epsilon naught, we have already seen from previous equations that this is nothing but the G value, okay. So E naught is equal to GTP, okay. So E naught is equal to G into T into P, and let me call this equation 15, okay. And in this equation, of course, G is equal to d by epsilon R epsilon naught. Of course, if you want to write it in the form of Gmn, you can write it as dmn divided by epsilon R epsilon naught. Here this G value is called the voltage sensitivity of the piezoelectric crystal, and this constant for a given crystal cut is given as Vm per Newton, okay. Now from this equation we have seen that E naught is equal to GTP, or G is equal to the voltage E naught by TP, okay. And please note that E naught by T is nothing but the electric field strength in volt per meter, okay. And this we can write it as G equal to field divided by the pressure or say stress. Alright. So if I denote E naught by T, the electric field at epsilon, I can write G as electric field by stress. This epsilon is our electric field strength divided by P. So let me call this equation 16. Alright. So E naught by T, we have seen that is the electric field intensity in the crystal, and P is the pressure or the applied stress in the crystal. Therefore, the crystal voltage sensitivity G can be defined as the ratio of the field or field intensity to the applied stress, okay, and the unit is Vm per Newton, okay. So we have the voltage sensitivity G and the charge sensitivity D, okay, and they are interrelated, okay. So G is equal to, or the voltage sensitivity is equal to the charge sensitivity divided by the epsilon R into epsilon naught, okay. And this is very important. Both the coefficients are very crucial for a piezoelectric material, okay. So two main families of constant, D constant and G constants, are considered for any piezoelectric transducer design, okay. So for example, for barium titanate, the commonly used constants are D33 and G33, while G33 is equal to the field produced in direction 3, while which is divided by the stress applied in direction 3, or E naught by T by the stress, which is force by the area, okay. And the voltage output is equal to G33 into F by A into T. We have seen already that it is G33 into T into P. So for any material, if G is known for that particular material, the voltage output per unit stress can be calculated by knowing the value of T. Once you know this, you can calculate the voltage sensitivity or voltage at the output, okay. In order to relate the applied force to the generated charge, the D constants are used, and one of the D constant can be defined as charge generated, say, in direction of say M divided by force applied in direction of say M. Or for D33, for example, you can write it simply as charge generated in direction 3 divided by force applied in direction 3. We have already seen that the first term suggests the electric quantity, and the second is the direction of the mechanical force applied, okay. And this is also equal to Q by F. We have just seen that Q is equal to D into F, okay. So D33 can be actually calculated from G33 if the relative permittivity of the material is known by the formula that we have seen, and the value of the crystal voltage sensitivity, permittivity and charge sensitivity, all these three are important for designing a piezoelectric transducer. And if you compare between say a natural existing piezoelectric material and a say poled or say artificially generated piezoelectric transducer, you can see a basic comparison between them, okay. For quartz, for example, it is of the order of say 50 into 10 power minus 3 Vm per Newton, while for barium titanate it is of the order of say 12 into 10 power minus 3, okay. So it is voltage sensitivity is a little smaller, but if you see the charge sensitivity, it is much higher for the barium titanate. So for quartz, which is naturally poled, you have the charge sensitivity of the order of 2 picocoulomb per Newton, while for barium titanate it's several times than this. So it is of the order of say 150 picocoulomb per Newton, okay. And similarly you can see the permittivity of these two material, okay. So according to the usability, the transducers can be designed by keeping these three parameters into consideration, okay. Sometimes it is desired to express the output voltage or charge in terms of the deflection rather than in terms of either stress or force. This is because it is really the deformation that causes the charge generation. Thus, we must know the modulus of elasticity of the material also for this particular purpose, okay. The equivalent circuit of a piezoelectric transducer looks something like this, okay. You can see that you have charge generator. The value of charge generator, this piezoelectric material itself is considered as charge generator, and the value is charge, say piezoelectric charge coefficient multiplied by the force, okay. So in this case, the source is a charge generator and the value of charge generated is equal to D into F, where F is the applied force, okay, and Cp and Rp are the capacitance and leakage resistance, and leakage resistance is usually little higher in this case, okay. The charge generator can also be replaced by an equivalent voltage source having a voltage of say E naught equal to Q by Cp, or Q we have seen that it is D into F, so E naught is equal to dF by Cp. This is in series with capacitance Cp and resistance Rp. So the charge generator can be replaced by an equivalent voltage source having a voltage of E naught, which is equal to Q by Cp. Q we have seen is equal to D into F, or E naught can be given as dF by Cp, and then you have to keep the other parameters in series with the voltage source that you have just replaced, okay. If you talk about the characteristic of a piezoelectric transducer, it has a very high output voltage and high output impedance, okay. It has a wide frequency response, and they are not basically suitable for static measurements, and mostly you will see that piezoelectric transducers are used in a dynamic applications because the charge will vanish within time, okay. So you will see that piezoelectric transducers are mostly used for dynamic applications, okay. The applications can be like in the pressure measurement, force measurement, vibration measurement, say for ultrasonic applications, microphones and so on, okay. Advantage over any other kind of pressure monitoring or other physical parameter monitoring device is that they are self-generating devices. You do not need any external power, okay. They can be made as small as possible because these are just crystals, okay. They are usually lightweight, and they can be used for high frequency response, and the constructions are very much rugged, okay, and they have wide dynamic range. So the disadvantage of piezoelectric transducers is one just I have mentioned, like it cannot be used for the measurement of static charges, and mostly they are suitable for measurement of dynamic responses, okay. They are very much affected by temperature and then require signal conditioning. You also require a special kind of amplifier like the charge amplifier for this kind of transducers, okay. If you compare it with the strain gauge, of course piezoelectric transducers are kind of do compete with the strain gauges. There is no power requirement, so basically they are self-powered devices, okay. Dynamic response is also much better as compared to the strain gauge based devices, and output impedance is also good enough, okay. So if I have to compare a piezoelectric transducer against standard devices like a strain gauge, I can say that these devices performs much better. Particularly the requirement from the end user. If you see, these piezoelectric devices do not require any external power source, okay. Although they are not suitable for static measurement, but their dynamic responses are very good, okay. Although the output impedance is little higher as compared to the strain gauges, so according to the need of the user, particular kind of transducer can be utilized, okay. So this is about a piezoelectric transducers. We have covered this over 2 lectures, and I hope that you have understood this kind of transducer. We will meet in the next class with a new class of transducers which are based on simple principles of transduction, like based on capacitive and inductive principles. Thank you.